So let's get cooking with the this lecture's topic. So the content of this lecture is about introducing you to the concept of energy system modeling, and I tried to gather these key factors to take into account to understand. And also we're going to look just a bit on the scenario side of the modeling. So this is something from last time we're going to go through still. So why do we do energy system modeling? The key components, that's also kind of a rehearsal. And then we're going to talk about this challenge related to this energy system modeling, so the accuracy and resolution of the models. And something about the model nodes, you'll probably understand those better when you're doing that SpineOpt simulation on the fourth period. And summary of key modeling and simulation concepts. So this is a good thing to keep in mind. I didn't pack everything in here, and also something about the scenarios and sources of data. And that's something we're going to go through tomorrow in the exercises, at least partially. We're going to go and see where to get data for these calculations and for these scenarios. So energy system modeling, why do we do it? It's a powerful tool for predictions. So that's what you're trying to do. You're trying to map out the future. It provides critical insight and strategies. And since we are at a transitional stage in our energy system, pretty much throughout the world, the most like the rate of growth of these renewable sources is so high that it's rapidly changing our energy system. So supporting decarbonization, that's the key factor. You're going to map out how fast you can grow these renewable sources and how can you mitigate the negative effect of those. So the fluctuation in the production. Addressing complexity. So the complexity arises especially for you in these calculations from not only the energy technologies, but from the sectoral integration. So you need to address many sectors in the working together in the models. Incorporating temporal and spatial scales, so accounts for variation across time, geography, short-term and long-term fluctuations. So those long-term models, they try to kind of predict, those are pretty much the scenario type models. So they are trying to look far into the future. And for that, you need accurate data from the history. And that nowadays is pretty much widely available. So you can go to various websites and download a ton of data and modify it, process it by yourself. So you can already have a lot, even though you're not working in any kind of an institution that has their own database and data bank, you nowadays have a lot of data at your disposal. It was totally different when I was a student myself, so we didn't have that open source data as readily available. So for example, you have the production data, you have the electricity wholesale price data, you have the weather data, and so forth. So modeling uncertainty, and this is where I'm going to show you some kind of a rudimentary, this Monte Carlo simulation, if we have time in the model. So managing uncertainty, how can you build a model up to kind of say what are the limits in which the system operates in? So this probabilistic approaches, it's not deterministic, rather it's stochastic or this probabilistic. You have variables in the model that they have a probability function. It can be this, it can be this, it can be something in between. And there's a probability at which a certain value comes up in the model. and that affects the outcome. Behavioral and social insights, so incorporating energy behavior transitions, models provide this realistic foundation for policies. And this is, in my opinion, a very important thing to get to the policymakers. You have to maybe not trust the modelers or models wholeheartedly all the time, but you have to go through the literature, what it says about the future predictions, what it says if we make certain kind of policy, what is the outcome of that in the future. So this policy investment guidance. And the key components that we went through last time, there's the energy source, which is the supply. Then there's the conversion, so that's the power plants, storage, transmission, and consumption, which is the demand. So this was the picture that I showed you last time. So there's the primary energy conversion, transportation, distribution, and final energy consumption. And your model can only survive with parts of this, so you don't have to incorporate every aspect of this, but usually you have some kind of a consumption. It can only be a scalar number. So at this moment, we have to produce 10,000 megawatts. So that's your consumption model. It can be based on data. It can be based on the actual reading at the moment. And then you have some competing primary energy and conversion sources that have a certain price. So you're trying to put them in a merit order, for example. And this can, in that kind of a model, this transportation distribution could be taken kind of for granted, so you don't have to model that separately. So the supply side incorporates, it has these traditional resources, coal, gas, and oil. And depending on the energy sector that you're dealing, for example, in Finland, we're trying to get rid of these in the electricity system, especially the coal and also oil. Oil is actually used as a startup fuel in a lot of the boilers. And if we have this more fluctuation in these CHP boilers, so the biomass boilers, they still use oil in the starter burners, at least most of them. So that would be an interesting topic to kind of calculate if the fluctuation of this electricity from the renewable resources increases, how does that affect to the oil consumption, because you have to start up the boilers, you have to run them down and so forth. Maybe not that much, but those are aspects that you can kind of inspect with these models. Renewables, wind, solar, hydro, geothermal, and biomass. Unfortunately, we don't have the possibility of making geothermal energy in Finland. There was a test in Otaniemi, this 6.4 kilometer deep borehole that made district heat, or was supposed to make, but there wasn't enough circulation in the borehole. So there's two holes that you drill in there, the injection and the or what do you call it, the suction side. So you inject liquid out from the other side, it goes through the porous ground, and then you pump it up when it's heated. But that didn't work out too well. So Finland doesn't have too good geothermal resources. Imports and exports, that's really important nowadays to take into account, since we have a lot of problems with the sea cables, as you've read from the news. So you always have to make kind of scenarios. What if somebody cuts the cables? How does that affect to our electricity prices, for example? Demand side, residential, commercial, transportation. So for example, this space heating, we're going to go through that later on. So what kind of models, what kind of techniques can you use for this residential space heating prediction? And of course, the transportation is heavily heavily kind of dependent on this oil. So how does that emergent electrification of those vehicles affect to the system? Conversion technology, generation, but also storages. Actually, I had a presentation yesterday on this Pirkanmaan maanrakennuspäivät, so related to construction engineering. And I was going through this Finland's energy storages. And at the moment, we're building a district heating energy storage of 90 gigawatt hours. So that is, I don't know if it's the largest in the world, but I think it's pretty damn near that. So, of course, there are electricity storages related to pumped hydro that are also in the 10 gigawatt range, but this kind of a almost 100 gigawatt hour, sorry, I was not referring to power in the pumped hydro, rather gigawatt hours. So this kind of a novel underground heat storage in, was it in Vantaa, up to almost 100 gigawatt hours. It's really unique. So we have to take those into account in the models. And CHP power. And networks, power grids, heating, cooling networks, gas and hydrogen pipelines. There was actually also a presentation on gas and hydrogen pipelines. So it was really nice to see pictures on how they are installing those hydrogen pipes. So it's about the size of this. So this DN100, DN70 pipelines that go into the ground. So that's in the next decade that has to be taken or has to be taken more into account. But of course, in the predictions, that's also something you can calculate. So related to these models challenge, how accurate do you want to make the model, and what kind of a resolution do you want to keep in it? So the temporal resolution, you can have hourly data. So that captures kind of a short-term load generation variability, including these intraday fluctuations. And most of the models that we are dealing in this course are with this hourly data resolution. You can also have this 15-minute resolution nowadays because the electrical market is going to jump up to this 15-minute cycle. Seasonal trends represent seasonal changes, higher heating demand in the winter, cooling in the summer, cooling in the summer. Multi-year scenarios. So this is something when you're trying to make these long-term scenarios and you're kind of using a lot of aggregated data and you sum up the data, for example, throughout the year and look into the 2050 year. Sub-hourly resolution. So this, of course, makes the model more complex, more heavy, but this gives you a lot of the ability to see what happens, for example, with the electricity prices, with the kind of how fast this is dealing, how fast the, for example, the CHP plants can keep up with the fluctuating energy demand. And this historical calibration, so includes historical data for validation and calibration of model trends. So that's something I'll try and show you with neural networks. It's an example from another course. Spatial resolution. So it can be local, capture citywide distribution systems. So for example, district heating systems are in this category because heat has to be produced and consumed on site. So it can only be transferred, let's say, a few tens of kilometers. So there's a distribution network for moving the district heat from the facility to the consumption, but it doesn't go from a city to another. So it's local. Regional considers cross-border interconnections, so regional grid dynamics and resource sharing. And then when the model goes on a really low resolution, you can calculate these global supply chains, for example. And this zonal node level represents power flows in specific zones or grid nodes for detailed modeling. And then you can have this urban versus rural. And regarding with the temporal resolution, it's good to know what kind of grid events occur in the electrical grid. So there are these protective relay operations that they are used to maintain the grid in a way that if some fast occurrence happens or fast, let's say, perturbation, disruption happens in the network, these are the ones that protect the network. So that's millisecond scale. One AC cycle, so you can calculate that based on the 50 hertz frequency. So what's the AC in here? It's alternating current. Inertial response. So what happens in the network? There's actually, let's say if there was, no, it wasn't in there. So inertial response, how fast this inertia starts to kick in when the frequency starts to change too fast. So this inertia is, for example, in the rotating generators in the network. So it tries to kind of resist the changes that occur in the network. And this frequency regulation goes hand in hand with that. There's variable energy resource deviations, demand response. So how fast, for example, if you saw the last time, I think I showed you the graph from FinGrid, the third of 6th last year when Olkiluoto 3 power plant tripped out of the network. So then this demand response immediately kicks in. Hourhead dispatch. So then we go into this hourly level and service restoration from outages. That's like hour to day level, day ahead scheduling, capacity markets. So you have to have like a planned amount of capacity at your disposal. TD planning, and now I checked what was the abbreviation for. So we're gonna have to see it like this: TD planning, and so yeah, transmission and distribution. So transmission and distribution planning, and planning for carbon goals. So based on what you're trying to model, what is your end goal in the modeling, you're going to have to set your resolution based on that for the model. So the challenge in terms of temporal and spatial resolution, the low resolution means that you have, for example, one node in your model, it's Europe, and then you have really low temporal resolution. So you may have a daily daily representation of the energy produced or consumed, and maybe this peak and night in there. And then if you have a medium resolution, you can go into the hours. So, and then you have multiple countries in your network. And when you're talking about a network the size of Europe, or the model grid the size of Europe, usually this is the kind of resolution that you would use. And if you would go into really high resolution, then it's about making these 15-minute fluctuation, maybe even 5-minute fluctuations, what happens. And that's something nowadays that you have to do, because the variability in the production is so high. And then you take into account multiple nodes and these, for example, these points in here in the Sweden shows that they have 4 different electricity pricing areas. So that's taken into account there. So how detailed do you want to go? It's mostly related to what do you want out of the model. Mostly, as I said, we are trying to deal with this hourly resolution in our models in this course. And these model nodes, they come into play, especially in the SpineOpt tool. So they represent points or locations in this energy system where various processes or variables interact. So they can represent generation units, transmission substations, distribution points, or demand sectors. And they kind of serve as these intersections where these energy flows are analyzed. So how much electricity comes from Sweden to Finland, and then you have the generation in Sweden, and then you have the generation in Finland. You have the prices, and what you want to do is you want to calculate how much flows between them. So serve as the intersection of where energy flows are analyzed. So decisions about optimizations are made, resource allocation, grid operations. So these generation nodes point where energy is produced, power plants, renewable energy sources, and so forth. Transmission node, where electricity or other energy forms, for example, heat or gas, are transmitted across the grid. And they connect generation sources to consumers. Then there's this demand nodes. So consumers or demand centers, residential, industrial, commercial, and so forth. And then there can be these storage nodes. So storage system, batteries, pumped hydro storage. It seems that in Finland, the magnitude of battery energy storages is about few tens of megawatts and few tens of megawatt hours. So you get a power in Lempäälä, for example. There's a power of 30 megawatts in the battery, and I think it was 36 megawatt hours. And you can see it in, it was in Pulikankulma, I think, next to this solar farm. So this is what it looks like in SpineOpt. The blue ones in there are the nodes. Try and hide this one. Yeah. So the blue ones are the nodes, and for example, there are this aggregated production, and it's connected to this node in here. And then there are these transmission lines, so it can flow in both ways. SpineOpt is an open source software in a sense, and for me at least, it was in some cases hard to kind of see what the representation was about, but you're going to get the hang of it hopefully in the exercises. So what the nodes help to do is to simplify complex systems, and in these optimization models, for example, the cost and constraints associated with each node, they're critical because they help to determine the most efficient energy generation and transmission storage, those strategies related to that. In our cases, we are talking about mostly the energy generation and transmission. I don't know if we have enough time in the exercises to include that in our SpineOpt model, the storages. In a power grid model, for example, the each node might represent this kind of a substation that connects generators and consumers. And the model would optimize the flow of electricity across these nodes. So how much from here to here, from here to here, and so forth. So the optimization is about finding the lowest cost of the system. More challenges. So the techno-economical details. So we went through spatial and temporal resolution. So related to this techno-economic detail, how much you are going to take into account these technology-specific costs, capital, operational, maintenance costs for various technologies. These can be found in various sources. I don't think there is any collection of every kind of production technology, so you kind of have to see through the net, and usually AI is going to help you with that. So find the CapEx and OpEx, capital expenditure and operational expenditure for a certain system. Learning rates. So cost reduction over time. If you have technological advancement, for example, building energy consumption, there are certain legislation, certain regulation that affects to that. And you can, for example, model it based on historical trends. So if you have an exponential decay line, how fast the energy efficiency improves, then you can use that. So learning rates is something to take into account. Fuel prices and availability. And that's also something, in some cases, it's hard to find any kind of an hourly or even daily data, but there are markets that you can look through for these primary energy resource costs. So gas, coal, maybe even biomass, but there are marketplaces that you can see through to get the price. Discount rates used to calculate the present value of future investments and operational costs. How to get that? Those are something kind of based on the market trends, and usually just the scalar number is used in those. Economic incentives. So inclusion of subsidies, taxes, carbon pricing mechanisms. So that's something that looks into the future. So you have something that kind of drives a certain development forwards, and you want to take it into account with these. Sectoral integration. So how many sectors you want to take into account? Electricity, heating, cooling, transportation, industry, buildings. They can be seen as one of those sectors, and also agriculture and land use could be taken into consideration. So for example, how much bioenergy production can they produce, land use constraints and carbon sequestration potential. So this land use change in forestry is something that heavily is affecting this carbon sequestration potential. So techno-economic detail, fully flexible power plants, tank model without self-discharging for electric storage, and only electricity sector taken into account. Then you want to take into account startup costs when you go into a higher resolution, startup costs for power plants. So tank model with self-discharge for electric storage. So if you have heat storages, if you have electricity storages, they might have these self-discharging nature. For example, this pumped hydro, which represents by far the most of the electricity stored in the world, by far, over 90%. So there's a self-discharging mechanism. Evaporation, for example. The sun shines in the pools, the water is being stored in, so it evaporates. There was actually this another type of this gravitational energy storage. And for example, in Finland, they're trying to make it in an abandoned mine. So 530 meters. So you have a mass in there. So you hoist it upwards and lower it downwards. So there's an electric motor and it can act as a generator. So whether you're lifting it up when the electricity price is low or lowering it down when the electricity price is high. And there are these kind of hotels for heavy concrete blocks. So you hoist them up and you transfer it to the storage. And in China, it was around 100 megawatts, I think, and 100 megawatt hours. Hopefully, I didn't recall that wrong, but somewhere in that range. So gravity energy storage, that doesn't have a self-discharging nature. So there it lies. It doesn't discharge the potential energy in any which way. So in that sense, it's a nice technology. Of course, it's really low energy intensity. Yeah, and then you might take into account more sectors in your models. And then you start incorporating these primary, secondary, tertiary reserves. You have a hot start, warm start, and cold start in your power plants, in the dispatchable power plants. And then you incorporate all of these different kinds of sectors into the model. So that's something about the resolution, modeling accuracy. And then we're going to go into these key modeling and simulation concepts. So these linear models, linear optimization, linear programming, mathematical models with linear relationship, well suited for large-scale system without complex interactions. And even though in some cases your model incorporates like polynomial fits, it doesn't mean that it's not per se linear model, because you're tracking kind of the variables only that affect the outcome in the calculations. For example, in that example that I showed you previously, I calculated the wind power production based on the third exponent of the wind velocity. But that doesn't exactly make it an unlinear model, because it's not per se a variable in that calculation procedure. It's something that I calculate before the actual modeling procedure happens. So in some cases, even though you are using these polynomial fits and higher or the logarithmic functions, it doesn't make it an unlinear model. So you have to kind of differentiate between those. So linear models, models with non-linear relationships, needed for more complex systems where behaviors are not proportional. This could be, for example, an efficiency of a partial load operation. Is it a straight line or is it a curved line as it is in reality? And when you go into these nonlinear models, it makes the complexity larger, but also how can you find those nonlinear relations? For that, you have to have a certain level of engineering proficiency. So you have to be able to calculate, for example, a nonlinear function of partial load and efficiency. Then top-down models, macro-level models focused on broad economic system-wide trends. And then there's the vice versa bottom-up models, detailed models focusing on individual components, technology-specific energy systems. And mostly we are dealing in this course of these bottom-up models. I have really low amount of experience with these top-down models. So they are much more broader. They have more qualitative aspects in them. So, but it's good to know I tried to make some kind of an example of that bottom-up model for you to kind of understand what it means. There can be calculation in that, and usually there is. It's not something that you kind of sketch out anything and leave the calculation for the bottom-up models. But the top-down models are more qualitative in nature. Simulation models or optimization models. You can use a simulation model as a tool for this optimization. So it's just making a conceptualization between what is simulation and what is optimization. Optimization deals initial values for the simulation model, and then it sees into which direction a certain variable is heading. For example, the overall cost of a system. The optimization models, they deal a certain amount of, based on the constraints, They deal, for example, to the gas power plant, you produce this much, and then nuclear power plant, you produce this much, and then you see what's the overall cost, and you try to minimize it. Deterministic models, models that assume predictable and certain outcomes based on known inputs. So the inputs are always the same, and there are no probability functions within the model. Vice versa, the probabilistic, the stochastic models, they take into account the fact that there is uncertainty, for example, in the initial values. So then your output is changed based on that. So there is randomness in the model. These linear models, both the objective function and the constraints are linear. This means that the relationship between variables are proportional and additive. So a mathematical model in which the output is a linear combination of the inputs. So output is a linear combination of the inputs. There can be something that you calculate based on polynomial fits, but these outputs and inputs are the ones that matters in the model calculation procedure itself. Example, optimizing energy generation with linear cost functions and constraints on capacity. Optimal production schedule for a set of power plants. Easier to solve computationally. So if you have large models, most likely they are going to be these linear models. If we don't get these quantum computers up and running, we are going to be facing the fact that there is a calculation constraint in our machinery. But of course, they are not as accurate when dealing with systems with these really complex relationships. And these nonlinear models, so relationships between variables are more complex, and this is where the differential equations, for example, come into play. Model includes non-linear terms. So at least one of the variables or equations in there that is used to calculate the actual outcome. Energy storage systems. You can have the relationship between energy stored and the discharge efficiency that is non-linear. So when you're calculating it, the next time step, you have to take into account that non-linear nature in there. We are making such small models in this course with Excel and maybe MATLAB or Python that whether it's not linear or non-linear, there's not too much of a difference in terms how much you have to make or how much you have to pay for it in the calculation time. So this, of course, has the advantage of being much more in tune with the complex behaviors of the actual behavior of the world, but computationally expensive. The top-down and bottom-up models. So the bottom-up models start with this kind of a engineering approach, and it starts with a really small level of technological detail. For example, you have the power plants, and then you start calculating their efficiencies and so forth. Sectoral disaggregation. So you calculate each sector by themselves, and then you start playing with their interconnective nature or variables. And at the top in here, policy analysis and impact assessment of technological energy mix within a sector. So you can assess something like that. This top-down has more of an economic approach, market equilibrium, higher sectoral integration. And I really had to, this is from a book, so I really had to see this through with an AI. Endogenous representation of macroeconomic parameters, and hopefully I'll get it right when I'm explaining it, and it's actually what the writers of the book meant. So, for example, in the model, gross domestic product can be exogenous input, so you can take it from elsewhere, or it can kind of be calculated based on the model itself. So endogenous representation of macroeconomic parameters. So the model itself kind of calculates the change in, for example, GDP. And the top-down models, if we conceptualize it, modeling always starts from this macro perspective, national, global level. Analyzes aggregated behavior of the system. So aggregated, I'm not sure if you're familiar with that word, but you bring in a lot of data together, aggregated, so sum it up together. These models, they typically use, for example, historical data, trends for future scenarios, and economic system-wide assumptions are made. So you're not talking about power plants in there. You're talking about, for example, the district heating system, and you're talking about how much the district heating system has to increase its production based on, for example, population growth. Economic-based models that forecast energy demand, pricing, and emission reduction scenarios using national economic factors and so forth. And they are good for policy analysis, long-term planning, works with aggregated data, but they lack really the detail in the models. Bottom-up models is something that you're going to be making in the spine-up, for example. Of course, these aren't, if you're drawing a Venn diagram on these, they can overlap on certain models. This spine-up, you don't say it's strictly a bottom-up model. It can have aspects of this top-down model. So focus is on details. And this is something that you are mostly familiar on this course. So technology-specific optimization. Models that optimize energy generation, storage, distribution, or on the level of individual power plants. So individual assets in the model itself. Highly detailed, suitable for modeling specific technologies and systems. And of course, computationally intensive. So let's have top-down model example. This is a really, really simple example, but this is just to kind of to get the hang of it. I have to say that when I'm trying to learn these new concepts and new things, whenever I see a YouTube video and they have an hour-long explanation on really complex model already, then I'm losing interest. So I want to see always what's the simplest model or simplest version of that model. So this is what I could come up with. So estimate the future demand for district heating in Tampere. So we're not talking about national level. Rather, we're talking about city level or region level. But it's not an individual power plant. We're not going into that specific details or heating plant, rather. So gathering the macro level data, we have to kind of decide what we want to include in there. So for example, population growth. We have to have some kind of an estimation for that. And you have sub-models for these. I just kind of pulled it out of my sleeve. So Tampere's population end of 24, roughly 250, 250,000 rather, with an increase of 5,000 compared to the previous year. So we can calculate some kind of an exponential growth based on that. Tampere's district heating demand in 2004 was roughly 2,000 gigawatt hours. And remember the new novel heat storage in Helsinki or Vantaa Kuusikonmäki, I think is what it was the place under Kehä Kolme. It's going to be close to 100 gigawatt hours. So it's massive. Energy efficiency of building heat consumption has improved 1% per year. Where can you get that? Well, that's something you can kind of deduce based on the rakentamismääräykset. Man, what's that in English? The regulation related to this building construction that says how much insulation you have to put into the walls. That's one way of kind of assessing it and seeing what's been actually done. That 1% just, I dropped it out of my sleeve. Assume a steady annual exponential growth in the population. Assume that per capita demand is affected only by energy efficiency improvement. And of course, we have to exclude some things. There's climate change, and you can get rather accurate model predictions what's going to happen to the average temperature. Of course, those are only predictions. But if you're talking about in a 20-year scale, you want to take into account that the climate is most likely going to be slightly warmer in our country. So on a general level, it means that less production is required. But since we're talking about 10-year level next decade, then we don't take that into account. So calculating future population growth of 0.02% or 0.02, so 2%. And where did I get that? I divided 5,000 by 250,000. And then to the power of 10. So exponential growth, that was an assumption. Based on what? Well, that's the population growth model, submodel that you would have to devise. So you have the future population. Then you estimate future district heating demand. And what we said that the only thing that is going to affect per capita demand is going to be the increase in, let's see, how did I call it in here? So increase in the efficiency of building heat consumption. So energy efficiency is improving 1% per year. So 1 plus 0.01 to the power of 10. We get per capita future demand, and then we can calculate what's the per capita demand at the end of the examination time times the population. So we get 2,207. So it means that there's roughly 10% increase. So you have different submodels in there. You have different subtasks that you need to solve, but we're looking things on a really general level. So the considerations, advancement in building insulation, heating technologies could reduce per capita, potentially offsetting some of the projected increase. So if the increase in the efficiency is larger than we expected. Renewable energy integration. That doesn't necessarily mean that it might be contributing to the system's efficiency and sustainability. Mostly you would have to calculate the efficiency effect of that renewable energy. So if you change, for example, from combined power plants to this CHP bio boilers, it means that the power to heat ratio of those systems goes down, but does it affect to the overall efficiency? That's something you would have to calculate. Policy on a general level. Policy impacts, so that's something to be taken into account. Top-down modeling approach is somewhat demonstrated in here, utilizing macro-level data for future demand forecasting. So you have to incorporate factors of outside temperature development, the weather data, that is climate models, changes in industrial activity and so forth. So that's something that you have to gather, but it's not on a really individual factory level. So a top-down model was there. The bottom-up version was, for example, the one that I showed you before. So this is really a bottom-up modeling approach. So this was the NATO off-grid production. So there was 2 diesel generators. There was solar and wind production, battery, and then there was this kind of a consumption. And the consumption is something that it's a non-linear model that I used for the consumption, but that doesn't make it a non-linear model when I calculate the energy production. So in a sense, this is still a linear model. I have non-linear elements in there, but they are kind of, before the actual calculation starts, they are used. So this was a simulation where I could change the battery size. So if I put a 5 megawatt hour battery, you see that there's a lot more curtailment being done in here. And then if I increase the battery size, then I don't have any curtailment, but there's still something missing from here. I could change the initial state of the battery so more inputted, more energy rather is input into the system in the beginning. So what I can do with this is, this is a simulation model. This is a bottom-up simulation model. That's I would say that it's a linear model in nature. It has some non-linear elements in it, but in some cases, it might be even rather hard for yourself to see that whether this is totally linear or non-linear. But beyond that point, this is bottom-up model. This is a simulation model, and I can attach an optimization model for it. So the optimization, this is something that we have done in our previous courses. So you might have one optimization variable. I say that battery energy is 0. How much do I have to use the diesel fuel in here? How much costs? This is costs per day, so it's really low in euros. Because I have calculated if I put diesel, there's the price for it, and then if I put a battery in there, I put battery of 1 kilowatt hours. It changes the system, it reduces the amount of diesel that I need in there, but it also gives me costs based on the annuity factor, so the investment cost, capital expenditure. So it decreases this operational expenditure costs because less diesel is used in the generation, but it also increases my capital costs. And this is an optimization algorithm that I used for it. So this is just a brute force. There's no like fancy optimization done here. I'm trying 0 kilowatt hour battery size, and the system cost is this. And then I put 1 in here, and the system cost is that. Then I put 2 in here, and the system cost is that. It's different because I have a different energy 0 in there. But either way, this shows me that the optimal battery size with these initial values is somewhere around, let's say, 11 or 12 kilowatt hours. That's the optimization part. I needed a simulation model to get the optimization done. So you have a simulator and you have an optimizer. In this case, I had a really brute force optimizer. It just had a hammer. No sophistication, none whatsoever. But it was nonetheless naive optimization, just trying things out. So simulation models, what they do, they tell you what's happening in the model with a certain set of initial values. And models and mimics the operation of a system over time. So we had 1 day. Explore possible outcomes under varying initial conditions, so initial values. Simulating the integration of renewable energy sources, for example, in that kind of a system, and including a battery. Advantages useful for exploring or the real world behavior rather, and testing different scenarios. Does not provide always optimal solutions. So if you have a really complex system, you have to have a complex optimizer also to accompany with it. You can find suboptimal solutions. You can find these local minimums with the optimizer if it's not sophisticated enough. So the optimization model itself, I could use the Excel solver to do the exact same thing in this Excel model. I could ditch this optimizer. There's a macro behind that. But this is my cost function. I have devised it based on the diesel generator operating costs and the battery capital costs. So I want to minimize this by changing this. So let's try. I have a solver in Excel. There's also an additional part in here. So solver, I can say that minimize this number in here by changing this number in here. And let's make unconstrained variables non-negative. So that's a constraint in there. I don't give any other solution for it. And okay, let's reset everything and hopefully we'll get it done. Well, this is going to be some demo effect. What should happen in here if I change this and solve this? It should find some sort of a solution, but I don't think I trust that. Something happened. So the optimizer wasn't too sufficient or too successful in its tasks. But what should have happened is that it should have found the minimum of this. Hopefully I didn't put maximum in there. Let's still try once more. Yeah, I think now I know what the problem is. I have the randomness factor in here. So let's try again. Yes, now it worked. So I had the random option on in there. But now it found 11.67, and now it's pretty much the same as in my brute force optimization. So Excel has some optimization tools, but in most cases they are not sufficient. So mathematical models that aim to find the most efficient, effective solution, efficient or effective solution. And what that means is that you have to be able to devise a cost function for the optimization. Otherwise, it doesn't work. And my cost function was the cost of the system. Advantages can provide exact solution to specific problems and can be computationally expensive. Now it was a matter of seconds, but in real life optimization cases, it can be a matter of hours or days even. Deterministic versus stochastic modeling. So deterministic, you have the same inputs, you get one set of outputs. So if I turn out the randomness factor in my model, and this probabilistic or stochastic models, they incorporate uncertainty using probability distributions, for example, or just random numbers, generating a range of possible outcomes. So for example, here, rather than using this regression in here, polynomial regression line, so there's electrical consumption versus hours of the day of the year 2019. In your model, you could take one specific scalar number of each hour, or then you could see for each hour that there is a probability density function in here. That's what we kind of devised the last time. So the kernel density estimator could be used in here. So you could see that with hour 6, I have a certain probability of getting this number, and that number. So in your model, you can incorporate that. And it handles variability. It's computationally more complex. and it presents results as distribution or the scenarios, risk analysis. So let's go back to that Excel model. So what I could do in here to incorporate this stochastic element is to put on the random number. So what happens in here if I put, for example, 6 in there, now you can see whenever I hit enter in here, it changes because the randomness factor, how did I do it? I have a normal distribution and I subtract random numbers from it. So what that kind of tries to mimic is cloudiness or changes in wind speed. So there's a probability density function for the wind speed and also some kind of a probability that there's going to be clouds. So what that means for my outcome is I can make a Monte Carlo simulation. So what that means is I have a certain amount of simulations. In Monte Carlo simulation, if I want to have a really nice probability density function from the outcome, I have to do many more simulations. But this is Excel, and in Excel, everything takes time. So what I did here, I have a macro that runs that it just gets the diesel generator energy from here and the curtailed energy. I'm not even using the curtailed energy. If I start it, it just presses enter in here, and these numbers change, and it stores them in here, and stores the second number in here, and so forth. And let's see if I start the macro. Whenever I use other programs with it, it's going to take time, so hopefully it's going to be done by the end of this lecture. But what it does, it always changes the random factor in there, and I get a probability density function, how much of that, yeah, that didn't work out. Yeah, most likely because I changed the inputs of my system. Let's put a bit bigger battery size and let's try that again. And fingers crossed, whenever I change something, even though this is a rather simple model, the outcomes is something that I can't kind of predict without testing it. So let's hope we get a nice probability density now. Yeah, there we have it. So what this represents is a probability density on how much I didn't put the axes in here. So that's the probability density, and that is how much in kilowatt hours would I use the diesel per day. So the biggest probability is that I need around 20, how much? 22 maybe kilowatt hours of diesel energy per day. But there are days in which I need less, and there are days in which I need even 25. So that's sizing of the system. And that's just really simple, this idea in this Monte Carlo simulation. So you vary the initial variables based on some randomness factor, probability factor, and then you see how the outcome changes. So you see that how much do I have to have this diesel fuel in store for this kind of a bad day? So the real problem is, how would you determine this probabilistic function for the cloudiness? That is what you need historical data for. It's not something that you could conjure up just like that, what I did in here. How much time do we have? Rather much, yeah. So that's a really simplistic way of this Monte Carlo simulation. And again, the hardest part of that is determining, because I had these randomness factors. So what I mean by that is whenever I change this system, I have this random factor on, but what that does, it scales so this rand 40. It means that up to 40% I can take out of this probability or the this normal distribution. So without the subtraction, the solar production would look something like that. So that would be all the way sunny day. If I put 10 in here and put the randomness factor on, it only subtracts a small part of the, so there's little cloudiness. If I put 40 in here, it's going to subtract much more. So how can I determine that? I have to have some weather data. I have to have data on the solar radiance. And based on that, I can determine those ones. So that's the real hard part in it. So that leads us into these scenarios. So that was kind of a scenario that we did based on this Monte Carlo simulation, that we had some kind of a probability function. So it was just random numbers that we subtracted from the initial solar radiance, and that changed our system. So it gave us a chance to kind of see what if. So energy system modeling scenarios are structured representations of potential future states of an energy system. So that's what we basically did there. Created to analyze how different variables such as solar and wind production technologies, policies affect the system's performance. So how much diesel do you have to have for one day? Used to explore a range of possibilities and guide decisions making in energy planning. So they have a really exploratory nature. What if questions, such as what if renewable energy targets are increased? So that's something that you could use in a top-down model. The effects might trickle down into this bottom-up model. But the top-down models could use this. What if renewable energy targets are increased? How much more wind power would we need to install into our system? What happens if energy demand grows faster than expected? Again, this is more like a top-down model scenario. So you have to see our hydrogen economy starts kicking on or kicking off, starts increasing. Then what happens to the industry? So you have to have these links between the sectors in the top-down model. You have to have links between the gas and the industry sector. Comparative framework. They provide bases to compare outcomes across different assumptions, such as technological advancements, policy interventions, fuel price fluctuations, or solar and wind fluctuations. So if you're going into a really detailed model, as my simulation in there was, then you can see what's really happening with the range of variables that you give it. These scenarios, now we use this kind of a probabilistic, stochastic modeling in there, but they can be also this deterministic. We change input variables. What if I have a smaller battery? What if I have a larger wind turbine? What if the whole country's electricity generation increases by 10% by the end of 2030? So small scale, larger scale, top down, bottom up, deterministic, probabilistic, or some combination of these all. Remember, it's a Venn diagram and they can be overlapping. It's not just one or the other. Time horizons. Now what we did, we had a 1 day horizon, time horizon in our small simulation. So short term, 5 years. I would say short term is 1 hour, 1 day, and long term, 20, 50 years. Strategic planning for sustainability and decarbonization. Operation or tactical planning. So what do you need to buy? And 1 day, it's more like how do you need to operate your system? How do you need to manage your system? How much diesel you have to have in the store? There are certain types of scenarios, decarbonizing scenarios, focus on achieving specific emission reduction targets. So this net zero by 2050, technology-specific scenarios, adoption of particular technologies like hydrogen, battery storage, or nuclear power. Policy-driven scenarios. We had this mäyräkoira, sausage dog, how do you call it? Sometimes when it would take it out to a jog, it was like, I don't go anywhere. But that was what Germany did with nuclear power. It's the same without doubt. After Fukushima, they made a policy-driven decision, which resulted in a scenario that Germany's, well, this is 2020, but by 2023, I guess, all nuclear power plants in Germany were shut down. So you could not see that in 2010, but after Fukushima, that was a reality. But you can explore such possibilities in an energy system with this energy system modeling and scenario creation. So that was a reality after that. So of course, when the decision was made, then the energy system modelers started to make models on how could that be, how the effect could be mitigated. They can be crisis scenarios. So if ships from unknown origin come and cut our cables, or the what was the, I'm having a blackout. What's the gas line in there? Nord Stream, yeah. The Nord Stream. And of course, the conspiracy theorists had a lot of things to say about it. Was it Russia? Was it USA? Was it CIA? So you want to look into that more. That was fascinating stuff, really. And there was a lot of methane that was actually pumped out of there from the hole. They had to empty the entire kind of pipeline. So crisis scenarios. What happens if our electricity connection lines are cut? It has a profound impact on our system, on our price, especially if the one between Finland and Sweden, somewhere around Turku and Stockholm, it's not exactly those cities, but somewhere around there, 1,300, 1,400 megawatts of electricity. And they're really vulnerable, as we see. All it takes is one ship and one anchor and drag it down for 10 kilometers and up you go. Crisis scenarios. Market scenarios explore fuel price changes, market liberalization, or shifts in trade dynamics. For example, that we don't do trade anymore with Russia. Well, usually there's a baseline scenario, business as usual. So reflects the continuation of current trends without significant policy or technology changes. So this is, I didn't have any caption in it. So it's this from EU reference scenario 2020 energy, transport and greenhouse gas emissions. Trends to 2050. So what happens towards 2050 in Europe? So this is total energy consumption in transport by fuel. Business as usual. What's going to happen? Fuel mix in transport. Then drivers. So yeah, alternative pathways. So incorporate different assumptions about renewable energy integration, electrification, energy storage deployment, and so forth. So what you have to take into account also is the drivers and constraints. What are the driving forces? And usually when the master's thesis students start to make some kind of modeling, this is always what I tell them to do at first. So you want to see what's driving the development towards this certain pathway, this certain technology that you are trying to pursue in the modeling. So demand growth, economic conditions, technology costs, policy measures. For example, solar panels, the cost per produced energy unit has gone drastically down and it's still decreasing. I'm still waiting for the day when I can get paint and, paint the wall with solar panel paints and, attach some wires in there and get the electricity. We're not too far from that. I mean, it's become really, really cheap to make these solar panels. And it's decreasing all the time. So how is that going to affect? So that's going to be a driver. That's going to be a driver for increasing this renewable electricity production. And that's going to be a driver in increasing electricity production where the frequency related to the Fourier spectral analysis would be that it spikes every day. So rather than wind being a bit more irregular, you would have really regular spikes every day. And the outputs, for example, it can be energy mix scenario of strong electrification from this AFRY Finnish Energy Low Carbon Roadmap 2020. So the outcome can be this kind of an energy mix. So this is what's happening now. And then you have a scenario where there is strong electrification. There might be a scenario where there's lower amount of electrification. There are drivers that are affecting to these overall outcomes. But for example, this wind production, you might, this isn't on subsidies on wind power, but there might be subsidies, for example, in the hydrogen industry. So that means that if the hydrogen industry starts increasing, it means that they need more cheap energy, electricity, and that means wind production is also going to increase. So it might be a certain scenario where policy changes or subsidies affect to it. Or then there is some market innovation that wind power is just going to be so cheap that it's going to increase like that. So that could be the outcome. Energy mix, that it is. Costs, emissions, system reliability and flexibility. What you're trying to kind of decipher. Something on neural networks. Have you heard about neural networks? I'm going to come to your door with a hat and a briefcase. Knock, knock. Do you have time to talk about neural networks? All the large language model used based on, or the work based on that. So they are increasingly used in energy system modeling and scenario analysis. Ability to model really these complex non-linear relationships and relationships that you don't even see by yourself. The model is going to find out. You can feed a lot of non-relevant data to it. It's going to ignore it. If there's no correlation between that non-relevant data and the output, those neurons aren't firing. There's no kind of problem with that. So this artificial neural network architecture is in a way that you have input layer, you have these hidden layers, and you have the output layer. Output layer doesn't mean that it's only one variable. This isn't the only kind of architecture. They can be circular, they can be any kind of pathways. But usually it's represented in this kind of a feed-forward network. So you have input layer, you have hidden layers, and you have certain amount of outputs. And then what's happening in one neuron is from these input layers. Let's say you're trying to recognize a cat. You have a picture of a cat. You're going to divide it into pixels. And all of those pixels have a certain RGB, red, green, blue value. And you input those into here. Then if you show this is a cat, this is a cat, this is another kind of cat, this is Siamese cat, this is Persian cat. I don't know cats. But whatever, you have a lot of pictures of cats. It's gonna, and you say that it is a cat, so 1 and 0 would be, for example, a dog. So it's gonna learn if you train it. And how you train it is by adjusting these weights and so-called biases. So there's gonna be a bias, there's gonna be weight, and an activation function. And what that enables you to do is that you can train the system in a way that when you show the picture of the cat, these certain neurons are activated. And And this calculation it can be 0 or 1 or something in between. It goes closer to 1. And the whole bloody large language model system functions on this procedure. The hard part is making these, adjusting these weights and biases. But either way, that's something I want you to kind of look from the internet and maybe make one of yourself. Most likely we're going to do one example also on the calculation exercises. It's really simple making them nowadays. Just you type into AI, give me fast forward neural networks, inputs here, outputs here. Go. And that's it. It's a few lines of code. So energy demand forecasting. They're widely used to predict energy consumption patterns, input variables, historical energy data, weather conditions, economic indicators, and so forth. Renewable energy integration, so they can be used to model the variability of renewable energy sources. There's these activation functions, so if you want to dive a bit more deeper into them, this Siiri Lampela's master's thesis, long-term electricity price forecasting in Finland, neural network model under demand and production scenarios. It covers pretty much the whole topic of this lecture. So applications, again, energy price forecasting, and that's what Siiri made. Grid management, scenario analysis, and policy development. So there's actually a video from VTT on this, what's the role of artificial intelligence. So it is this neural networks in the future of energy systems. I'm going to show you just a quick example in MATLAB. This is what we did in power plant engineering. So now what I have in here is I have a system in which I am inputting data. So from 2020, and what the data is like, let me see if I can find the folder. The data is like this. I have a certain step. This is the hour of the hour at question. Lämpötila, temperature, tuulisuus, wind. I just took random places from Finland. Random places from Finland. Because that kind of represents what's happening in the whole country. This is from the western side of Finland, so from the coastline where the most of the wind power is. Then I took from Ensoe, so this is from Ilmatieteen laitos, Meteorological Institute, and this is from Ensoe. So how much every asset is producing at that hour. So that these are the inputs to the neural network, and this is the output, electricity price. And the whole code for that is pretty much in here. So generate a neural network, set training parameters and train network. That's it. MATLAB does the rest. So you only have to know what's the input, what's the output. And now the interesting part, of course, is that this is how well the neural network kind of learned. How do the input variables correspond to the electricity price in the year 2020? And it's rather close match. It kind of finds the relevant patterns from here. Really nice. I had a really small set of inputs into it. But this is what happens in 2021 because of after Corona industrial resurgence. It doesn't know what's happening. I didn't give any data for it that, oh, there were, I don't know whether wars during that time, but there was an energy crisis in which fuel prices were rising. I didn't give that data to it, so it didn't learn based on that. So that's why this is a good example on how neural networks fail. You fail to give it sufficient amount of data. But either way, if you were to give that data, you were to get some results such as Siiri in her master's thesis, and they were rather spectacular. Where was I? I was in here. Sources of data. We have 3 more slides. Don't worry. We're going to get through. Sources of data. Where do you get this information on? National, regional databases, international organizations, grid operators, open power system data. Well, the ilmatieteen laitos is in a wrong place there. It's not power system data, it's rather meteorological data. Research and academic sources, industry reports, and I have sources in here, so you can click these. For example, Ember. Since ENTSO-E doesn't provide any novel electricity data, European wholesale price data, and I'm going to click from here, hourly electricity prices, and this is universal coordinated time. I'm going to check this. There are all the countries, so let's take Germany. And there are, so this is the comma delimited form, but you have from 2015 till, 2025 each hour, and all the countries. You don't have to, that's a really good service in my opinion. That's like perfect. Then there's Finnish Meteorological Institute. From there, you can get solar irradiance, wind, how much rain, and so forth. Hourly or even 10-minute scale. ENTSO-E. So that's the transparency platform. And there's electricity price data, there's generation data, there is capacity data. You have to register there, but that's free. FinGrid, open data. If you want to get really detailed information on Finnish wind power, for example, how much is the capacity at right this moment? How much is the production at this moment? What is the prediction for tomorrow, and so forth. And this was the open power system data and renewables ninja. So that gives you, for example, let's take wind power dataset Merra, and can I take the country from here? Was it so? There, country, Finland. And it's going to give me, for example, wind current fleet or capacity factors should be here as well. But there's a lot of data. You can check that out, and we're going to see that in the exercises. So key challenges: data availability. You might not get access to some data. Uncertainty. Future developments, policies are inherently uncertain. Complexity. Diverse data sets into coherent models requires technical expertise, as you're going to see. There's always some hours missing. There's always some, summer, is it summer and winter solstice or something like that? There's always one additional hour or 1 hour missing, and you have to make a lot of processing of the data. So by gathering the right data and robust scenarios, energy system modeling can provide critical insights and pathways, but you have to have the right kind of data. Usually the data sets that gather like aggregated data from all countries, like this renewables ninja or ENTSO-E, they don't have the exact numbers. You want to go to the national databases. So if you want to make Finnish energy system model, then you want to have Finnish national dataset to get the data from.